Hi, this is Schwartz from MasterMathMentor.com. This is video BC16. The topic is sequences and it covers the BC manual pages 89 and 90. Hi, this is Stu. The last major topic of BC calculus is sequences and series. In mathematics, we define a sequence as a set of numbers that has an identified first member, second member, third member, etc. It is a function whose domain is the set of positive integers. But rather than use standard function notation, we use subscript notation because it better defines the sequence. So the first member is a sub 1, the second member is a sub 2, the third member is a sub 3, the fourth member is a sub 4, and so on, and the nth member is a sub n. And we will write this as a sequence denoted by the set of a sub n. Sequences are given in one of three ways: explicitly, recursively, and the first few terms. When a sequence is given explicitly, the rule to calculate the nth term is given, and by plugging in the numbers 1, 2, 3, etc., students can generate the terms of the sequence. The advantage of the explicit form is that students can determine any term of the sequence simply by plugging in that number. You want the 50th term? Plug in 50 to the expression. Given our three sequences given explicitly, and you are to write the first few terms of the sequence. In A, you are told that a sub n equals 4 plus negative 1 to the n. When n is 1, we have 4 plus negative 1, which is 3. When n is 2, we have 4 plus 1, which is 5. When n is 3, we have 4 plus negative 1, which is 3 again. So this sequence is 3, 5, 3, 5, dot, dot, dot. In B, b sub n equals 3n over n plus 1. When n is 1, we have 3 over 1 plus 1, which is 3 halves. When n is 2, we have 6 over 3, which is 2. When n is 3, we have 9 over 4. The next term is 12/5, and we continue on. In C, we're told that c sub n equals n squared minus 1 over 2 to the n minus 1. When n is 1, we have 1 minus 1 over 2 minus 1, which is 0. When n is 2, we have 4 minus 1 over 4 minus 1, which is 1. When n is 3, we have 9 minus 1 over 8 minus 1, which is 8/7. The next term is 1 again. The next term is 24 over 31, and we continue. When a sequence is written recursively, a rule for the first term is usually given, and a rule for the nth term in terms of the n minus first term is given. From there, the sequence can be written. The advantage of the recursive form is that the pattern becomes absolutely clear. The disadvantage is that in order to get any one term, you need to know the term before it. So to know the 50th term, you need the 49th term, which means you need the 48th term, etc. Given our three formulas recursively, and you are to write the first few terms of this sequence. In 2a, you're told that a sub 1 equals 3, and a sub n is 2a sub n minus 1 minus 1. So obviously our first term is 3. The second term is 2 times the first term minus 1, which is 5. The third term will be 2 times the second term minus 1, which is 9. The fourth term will be 2 times the third term minus 1, which is 17, etc. In 15, b sub 1 equals negative 1, and b sub n equals b sub n minus 1 squared plus 1. The first term is negative 1. The second term is negative 1 squared plus 1, which is 2. The third term is 2 squared plus 1, which is 5. The fourth term is 5 squared plus 1, which is 26, etc. In C, c sub 1 equals 22, and c sub n equals the quantity c sub n minus 1 plus 2 all over 2. Our first term is 22. So the second term is our first term, which is 22 plus 2 over 2, which is 12. Our third term is 12 plus 2 over 2, which is 7. Our fourth term is 7 plus 2 over 2, which is 9/2, etc. Hi, this is Stu Schwartz. Sometimes you are not given the rule, you are just given the first few terms of a sequence, and you need to try and generate a rule A sub n that fits. There really is no hard and fast way to do this. It's a matter of recognition of patterns of numbers. Some of them can be quite difficult, but usually on the AP exam, you will only have to do obvious ones. Here are 6 that are relatively easy. In 3A, you are given the sequence 4, 10, 16, 22, ... It should be apparent that the difference between each number is 6, and you can think of it as a slope of 6. And to get the first term as 4, it would be 6n minus 2. When n is 2, the next term would be 10, etc. In 3b, you're given the sequence negative 1, 4, negative 9, 16, ... Whenever you see the terms alternate, you know that it will either be negative 1 to the n or negative 1 to the n plus 1. Since the first term is negative, negative 1 to the first would be negative, and therefore it is a negative 1 to the n. The numbers themselves are just the squares of n. So your sequence is negative 1 to the n times n squared. In 3c, we have negative 1, 2, negative 6, 24, ... Again, the sequence will start with a negative 1 to the n because the first term is negative and the terms alternate in sign. And the numbers themselves are just the factorials. So this is negative 1 to the n times n factorial. 3d reads 2 over 1, 4 over 3, 8 over 5, 16 over 7, 32 over 9, ... Whenever you're given a sequence containing fractions, it is usually best to think of the numerator and denominator as independent sequences. The numerator are just powers of 2, or 2 to the n, while the denominator are odd numbers, which is 2n minus 1. So the sequence is 2 to the n over 2n minus 1. 3e reads 1/2, the square root of 2 over 3, the cube root of 3 over 4, the fourth root of 4 over 5, ... The numerator are just the nth roots of n, while the denominator are the integers starting with 2, and that would make the sequence the nth root of n over n plus 1. 3f reads 1, 0, negative 1, 0, 1, ... The pattern is obvious, but coming up with a rule, not so much. But this problem occurs quite a bit, and you're going to need to recognize it. it really has to do with the trig function. In fact, it deals with the cosine function. We know that cosine of 0 is 1. The cosine of pi over 2 is 0. The cosine of pi is negative 1, and the cosine of 3 pi over 2 is 0. So this simply becomes cosine of n minus 1 pi over 2. Sometimes when you are given the terms, it is easier to write the sequence as a recursive rule rather than an explicit rule. Here are three such examples. In 4a, we're given 1, 2, 4, 8, dot, dot, dot. The first term is 1, and it's clear that each term is doubled the previous term. So a sub n equals 2 times a sub n minus 1. In 4b, we're given almost the same sequence, but this is 1, 2, 4, 7, dot, dot, dot. First term is still 1, and now the difference in the terms between the first and second term is 1, between the second and third term is 2, and the third and fourth term is 3. So therefore, a sub n will equal a sub n minus 1 plus n minus 1. 4c reads 1, 2, 4, 10, dot, dot, dot. This is a very difficult problem, and is only given to show you how complex these can be. Let's look at the answer and show that it works. The first term obviously is 1. The second term will be 4 times 1 minus 2 times 1, which is 2. The third term will be 4 times 2 minus 2 times 2, which is 4. And the fourth term will be 4 times 4 minus 2 times 3, which is 10. When you see the formula, it's obvious that it works, but determining the formula is not simple. Hi, this is Stu. Two terms that we met before are convergent and divergent. We will use them again while working with series and find that they pretty much have the same meaning. Sequences whose terms approach a limiting value are said to converge. So if the limit, as n approaches infinity, of a sub n is equal to some limit L, then we say that the sequence a sub n converges. As an example, the sequence 1 over 2 to the n, which is 1/2, 1/4, 1/8, 1/16, 1/32, dot, 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 will converge because the limit as n approaches infinity of 1 over 2 to the n is equal to 0. And if we look at the graph of the points, 1, 1/2, 2, 1/4, 3, 1/8, etc., we can see that this is getting smaller and smaller and approaching 0. Sequences whose terms do not approach a limiting value are said to diverge. If the limit as n approaches infinity of a sub n is not equal to some limit L, then we say that the sequence a sub n diverges or is divergent. As an example, we look at the sequence the square root of n, which is 1, the square root of 2, the square root of 3, 2, the square root of 5, dot, dot, dot. That is divergent because the limit as n approaches infinity of the square root of n is infinity. If we look at the dots, they're getting higher and higher without bound. In problems 5, we are given 3 sequences and asked to determine whether they are convergent or divergent and give a reason. In number 5, we have the sequence a sub n is equal to 4 plus negative 1 to the n power. It is always a good idea to write out the first few terms of the sequence, and we get 3, 5, 3, 5, dot, dot, dot. This oscillates between 3 and 5 and will never reach a limit, so this sequence is divergent. In 5b, we're given the sequence b sub n equals 3n over n plus 1. Rather than write the first few terms out, we will simply look at the limit as n approaches infinity of 3n over n plus 1, and we can use L'Hopital's rule to determine that this is 3. And since this is a limit that exists, this is a convergent sequence. 5c reads, the sequence c sub n equals n squared minus 1 over 2 to the n minus 1. We write out the terms and we get 0, 3 over 3, 8 over 7, 15 over 15, 24 over 31, etc. It is not clear whether a limit is being reached here, so we will do this by L'Hopital's rule. Looking at the limit as n approaches infinity of n squared minus 1 over 2 to the n minus 1, we get infinity over infinity, and when we apply L'Hopital the first time, we get the limit as n approaches infinity of 2n over 2 to the n times natural log of 2. We apply L'Hopital one more time, and we get the limit as n approaches infinity of 2 over 2 to the n times the natural log of 2 squared. And that is 0, meaning that this is a convergent sequence. Hi, this is Stu. Finally, some definitions. We define a monotonic sequence as one that is either non-increasing or non-decreasing. Non-increasing means the terms are getting smaller or staying the same, while non-decreasing means the terms are getting larger or staying the same. So in non-increasing, a sub 1 is greater than or equal to a sub 2, which is greater than or equal to a sub 3, etc. And in non-decreasing, a sub 1 is less than or equal to a sub 2, which is less than or equal to a sub 3, etc. In number 6, we have the same sequences that we had previously, and we tried to determine whether they were convergent or divergent. Now you are asked to determine whether they are monotonic or not monotonic. 6a reads a sub n is equal to 4 plus negative 1 to the n, and this sequence is 3, 5, 3, 5. It is not monotonic. The terms start getting larger and then they get smaller and continue the same pattern. In 6b, we're given the sequence b sub n equals 3n over n plus 1. The terms are 3 halves, 2, 9 fourths, 12 fifths, and the terms are getting larger, and therefore this is monotonic. To actually prove that, you need to show that 3n over n plus 1 is an increasing function. Take the derivative and you will find that the derivative will always be a positive number, meaning that these terms are getting larger. In 6c, we're told that c sub n is equal to n squared minus 1 over 2 to the n minus 1. We will write out the terms 0, 1, 8 sevenths, 1, and since the term goes from 1 to 8 sevenths and then back down to 1, it is not monotonic. We say a sequence is bounded from above if there is some number m greater than every term in the sequence. A sequence will be bounded from below if there's a number n smaller than every term in the sequence. And if a sequence is bounded and monotonic, then it must be convergent. In number 7, you are given 4 graphs and are asked to determine whether it is monotonic or not, bounded or not, and convergent. In 7a, it is clear that the terms are getting larger. And because of the asymptote shown, then this curve is bounded from above, and therefore it will be convergent. In number 9, this curve is bounded from above. It does not appear that this curve will ever get above 9. It is also convergent, as we find that the limit as n approaches infinity of a sub n will be 0. But it is not monotonic because the curve increases and then it begins to decrease. In 7c, this is indeed monotonic, as the points are getting higher and higher. It is bounded from below because this curve will never get below 0. However, it is not convergent, as the limit as n approaches infinity is infinity. Based on the evidence, we could say that this curve is neither monotonic, bounded, or convergent. It is not monotonic because it oscillates, getting larger, then smaller, then larger, then smaller. There is no number that will be larger than all its values or smaller than all its values, and the limit as n approaches infinity of the expression does not exist.